Hello and welcome back everybody to the lecture on multivariate Gaussians. Last time we talked about an operation that looks at the product between two Gaussian densities, and it turned out that the multiplication of two Gaussian densities results in a new Gaussian, and we introduced the so-called information form that simplifies this operation. Today we continue with two typical operations from probability theory. The one is marginalization. What does that mean? So assume we have a random variable x that is a Gaussian, and what we want to know is what's the density of some of its variables only. So we know that it's a d-dimensional random variable, and we only select a couple of those dimensions, so indicated by this set I of indices. And now we would like to know what is p of xi, and it turns out that this can be written as here. So the new random variable xi, so I representing the selected indices, is actually a selection matrix times the original random variable x. And now we know that this has to be a Gaussian, because, let's go back in our slide set, here we are. This is exactly the case that's written down here. You have a linear transformation of a random variable x that is a Gaussian. The new one is a Gaussian again, and it has this mean and this covariance matrix. And what you need to do now is to identify the form of this selection matrix and then simply plug it in, and then you will see that this is a Gaussian, as we just said, and that the mean of this new Gaussian is actually the selected mean values of the original Gaussian, and the covariance matrix is actually the selected part of the covariance matrix. And as an exercise, you should think of what is actually the form of this selection matrix. Obviously, it's probably a matrix that has only zeros and ones, and it has like d many columns and I many rows, probably. Okay, next operation that we are interested in is conditioning. So conditioning means I have a random variable x, and I'm assuming I know some of those, a multivariate random variable x, sorry, and I know some of those entries. And now I would like to know what's the probability density of the unknown, unobserved part of this random variable x. So again, I have a set of indices that I don't know the values, and I have a set of indices R that I know the values. And as it turns out, this is a Gaussian, and the question is, how does it look like? And well, I'm taking a shortcut here. This is a rather involved computation, but it is rather, that's the important word here, rather straightforward to figure out if you write down everything in natural parameterization, and then first of all remembering that you can always write p of x is in this form, which can be written with any case of I and R. And then you can read off the result after some algebraic reformulations, but these are not totally easy, and particularly it's not completely obvious how the moment parameterization looks like. If you're really interested in doing this, you need to look up so-called Schur complement, and then you can solve it in a couple of matrix reformulation steps on your own. But the solution is actually, well, it's a Gaussian and it has this mean and this covariance matrix. And what are these things here? If this is the original covariance matrix, then this is which is wrong. It should be something like this. Okay. Okay, so given these two results, which are somehow the cornerstone for this next slide, we will look at the so-called linear Gaussian systems, and well, this is rather straightforward. So we assume that we have a Gaussian random variable x with a mean and a covariance matrix. We also assume that we have a conditioned Gaussian y, so it's conditioned on x, and it has this form. And now you may think, okay, is this now a very contrived case, or is it something that's happening quite often? And as it turns out, these two formulae are the ones that you need to understand the so-called Kalman filter that you may have heard of. So the Kalman filter actually has two types of equations that look like that. The one is sort of a state update that has actually this semantic, so what's happening from t-1 to t with respect to my state, where x is my state, and the other one is actually what do I observe at state t, so that's yt, given that I'm in state xt. Okay, so these two formulae are actually of this kind. So if you understand how to solve or handle these kind of formula, then you know how to tackle the standard Kalman filter. And what are the questions that we're interested in when we see these two equations? Well, we would like to know what's actually p of x given y, so the inverse of this, and maybe, or usually, what's p of y. And without going into the details, because they would use all the things that we learned up to now, simply stating the results, and you can look those up. And it's also something that you probably do not need in this detail, at least in the next couple of weeks, but it's always good to know where these equations at least come from, roughly. So we can give p of x given y in this form. So it's a Gaussian again, it has this covariance matrix, and it has these this mean. And actually what you're doing here is, well, y depends on x, and if you're asking what's p of x given y, then what you're saying is, well, I would like to know x given that I have a noisy version of itself. So this is what is represented here. And how would you get to this formula? And as it turns out, well, what you actually do is that you introduce a helper or an auxiliary variable z, which is x and y together. And why does this help? Because, well, p of z, p of so with this decomposition, you can now plug in what you know about p of y given x times p of x. And now you see you need to know all those things of multiplying two Gaussians with each other. And after doing this and fiddling around, then it turns out that Z actually has this mean value, not very surprising, and it has this covariance matrix. And now you can simply use what you learned about conditioning and marginalization. So if you would like to know p of x given y, then you would look at this covariance matrix and simply plug in the necessary terms and collect everything together, and then you will get the formula from the slide before. Similarly, if you would like to know what's p of y, then, well, you're marginalizing p of x. Okay, so p of y marginalized actually means you're selecting only these entries and this covariance matrix entry or part. Okay, so it's here, and as you can see, this is exactly what's written down here. So this is p of y, and with the mean and with its covariance matrix part. So given these four formula, you're actually able to solve at least simple control problems and problems from robotics that involve the Kalman filter. So as an example, we are looking at this problem that may occur in robotics actually. So assume that you have a measurement device that tries to find out, well, where is a specific object, for example, in 2D or 3D. And assume that we know a little bit about the object X that we are interested in. We have some idea where it is, and this idea is represented as a Gaussian with a mean mu0, and, well, our uncertainty is represented by this covariance matrix. We also have a device that measures this X. So this device measures y I of X, so a noisy measurement of the true position, and this is written like that. So obviously we would like to have our sensor in expectance returning the true thing, and it has of course some measurement noise. So what is a simple example for that? Assume that you are a ship, and okay, actually you are moving into this direction. Okay, and here is some landmass, and here is the lighthouse. And now you're sending some beams out and trying to figure out where is the lighthouse. Of course, you have a map where you roughly know where the lighthouse is, but you also measure the position, and sometimes you get some measurements here, 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 and here. And now we'd like to integrate all those measurements and your rough knowledge about the position of the lighthouse into final measurement. And, well, how would you do this? And this is exactly what's written here. So if you would have only one measurement, y1, okay, then you can immediately apply what we wrote down on the slides before. Okay, but assume now that you have a couple of those measurements, what you do then. Of course, you could say, okay, I'm integrating those one by one. First, I'm taking the first measurement and integrating with the knowledge of x, and getting out of these, well, two measurements, or say one measurement and the knowledge about x, I'm getting sort of a combined knowledge. And taking this combined knowledge, I can now integrate the next measurement and getting a new updated knowledge state, and so on the forth. But well, this is one possible way, a sequential observation process actually. But what's happening if you have all those n measurements at once, and now you would like to integrate them, and then you look at the formula on the slides before, and then you see, okay, that's not exactly what I have there, right? Because there I have something like this. Okay, p of x given y, this is what I can answer given that I have p of y given x. But now I have like these n observations, and the trick here, and it's quite a valuable trick actually, is that what you need to do here is that you say, okay, I have that many measurements to start with, and given that I'm conditioning on x, I know they are independent. So I know this is like, and so on. Okay. And what you now need to do, and definitely this is a little bit advanced already for this state, but what you do now is that you write down the Gaussians for all of those n measurements and summarize, put them together into one new variable. So what you can do is that you integrate parts of these formulae here, and you can write one big expression that somehow has a new y, so y tilde, that's depending on x, and some other terms that are not depending on x actually. And then you have exactly this form of p y given x, and then you can, with this new y of course, and then you can apply this formula here. And as it turns out, this new y is actually the average of these n measurements. And well, there is not enough space here to write down everything in detail, but this should help you get started, and you know what you are aiming at, so try to figure this out on your own. The interesting thing is that the same idea, so here what we have is we have one sensor and we have n measurements, and of course this is this one sensor where we know how it errs, right, according to this covariance matrix. And on the other side, or the other hand, what you can do with the same idea is when you have different kinds of sensors with different kinds of measurement noise, and then you can do the very important sensor fusion really with the same algorithmic approach here with the same formula. Okay, so for us we end the multivariate Gaussians with a Bayesian look at the problem. So we can use everything that we saw on the last slide for a nice Bayesian treatment. And what we want to do here is assume we have a couple of observations for our true mean of our multivariate Gaussian. So we have n observations. Assume that we know the covariance matrix of these observations, and what we would like to know is what's the true mean value of our underlying Gaussian. So for Bayesian approach, we need a prior on our true value mu. Assume we know something. It's a Gaussian. It has expected value mu0 and covariance matrix v0, and this covariance matrix can be like very, very large very uncertain. And then what we can do is simply use the formula from the slide before, plug in everything, and this is the new result. So we get a posterior density on our mean value that's depending on the observed data points and our observation noise, and it has this mean value and this covariance matrix. And we finish with a special case. So assume that our price is basically infinitely large, so we don't know anything about, we have no prior information. If we plug in this assumption into the formula on the slide before, then what we get is that our posterior density of the mean value is a Gaussian with expected value, the mean of our observations, and the observation covariance matrix scaled down by those n observations. Right, and this makes a lot of sense if we compare this with our maximum likelihood estimation. It's consistent because this was our maximum likelihood estimate, and this is also consistent because it simply says the more I observe, the more certain I will get.